Welcome students to this hands-on session where we reinforce the theory from Lecture 1 through a carefully crafted set of exercises. These problems are designed not only to practice syntax, but to deepen your conceptual understanding of methods, control structures, randomness, and encapsulated logic in C#. Let's walk through each problem together, step by step, and uncover the principles they demonstrate. We start with a fundamental test of the math class in C#. For each line, you must understand what function is being called and why the result behaves that way. Math.absx gives the absolute value, so negatives become positive. Math.floorx returns the greatest integer less than or equal to x. Math.ceilingx does the opposite, rounds up to the smallest following integer. The final line is nested, math. Ceiling, math, abs, 8 plus math, dot floor, 5.5. This teaches you to read inside out, applying each function in the right order. This real-world scenario introduces custom method creation. You define a method calculate charges that receives a parking duration, applies a fixed $2 charge for up to 3 hours, adds $0.50 per additional hour, and caps the total fee at $10 per day. Students learn how to use math.ceiling to count every partial hour and practice using loops, cumulative totals, and user input. This is your first structured program with real logic and encapsulated behavior. Goal: create a function that calculates parking fees based on time. Explanation: we're told the first 3 hours cost a flat $2. If someone parks longer, they pay 50 cents for every additional hour, and no matter what, the total can't go over $10. So our method checks. Did the person stay 3 hours or less? Then it's a flat $2. If more, subtract 3 from the total hours to find extra time. Multiply that extra time, round it up, by 0.5 to find the extra charge. Add it to the $2 base. Finally, use math.min to make sure the total never goes beyond $10. This teaches how to combine conditional logic, rounding, and limits into one neat method. Here, we simulate rounding manually, using y equal math.floor x plus 0.5. This mimics the behavior of math.roundx, but allows control over how rounding is computed. It's also a great chance to practice loops, console input, and formatting outputs. Goal: round a number to the nearest integer using only math.floor. C# already has a math.round function, but here we're learning how rounding works from first principles. Here's the trick. If we want to round a number like 2.7, we add 0.5. It becomes 3.2. Now if we apply math.floor, it becomes 3. This method works in general for positive numbers. Adding 0.5 then flooring mimics traditional rounding. It's an excellent way to manually simulate a standard function, which helps when writing low-level or custom math code. In this task, you get familiar with the random class and its next min, max method. You learn how to produce integers in closed ranges, like 1 to 2, or 0 to 9, using correct upper bounds. Remember, random.next a, b includes a but, excludes b. Mastering this is essential for future applications, like games, simulations, and randomized testing. Goal: generate integers in specific ranges like 1 to 2 or 1000 to 1112. C# gives us a random.next, min, max function that generates integers starting from min and stopping just before max. So if you want a number between 1 and 100, you use random next 101, because 101 is not included. If you want a number between 0 and 9, use random.next 0, 10, and so on. It's a simple idea, but off by 1 errors are common. That's why this practice is so important. You're mastering how to use random numbers precisely, not just randomly. Here, you take randomness a step further. Instead of generating any number, you generate one from a specific set, e, g. And for the set 2, 4, 6, 8, 10 or, we write 2 plus random. Next, 5, 2. This shows how you can generate structured patterns using base values and steps. It's a clever use of arithmetic progression with randomness, a concept that pops up in simulation design. Goal: generate a random number from a specific set, like 2, 4, 6, 8, 10 Rs. Here, instead of just generating numbers from a continuous range, we want specific spaced values. We realize the numbers in that set are all even, starting from 2, spaced by 2. 2 plus 0 times 2 equal 2. 2 plus 1 times 2 equal 4, etc. So we use 2 plus 2 times random.next, 5. This gives you 5 options, 0 to 4, scaled into even numbers. Same idea for 1, 3, 5, 7, 9, just start at 1. This builds intuition for creating structured randomness, very useful in simulations and games. Now we introduce decision-making with conditionals. Given a student's average grade, you classify it into a GPA tier from 0 to 4. This trains you in writing clean if-else logic, handling numeric ranges, returning results from a method, and performing classification algorithms, a precursor to future AI logic. Goal: convert a student's average grade into a GPA point, 0 to 4. We're designing a method that receives an integer grade, say 85, and returns a number from 0 to 4. We break the logic into ranges, 90, 100, return 4, 80, 89, return 3, 70, 79, return 2, 60, 69, return 1, less than 60, return 0. We write this as if-else conditions, checking from highest to lowest. This is a classic categorization algorithm, a key pattern in AI, analytics, and data systems. Finally, we close with an interactive game. The program randomly picks a number between 1 and 1000. The user keeps guessing, and the program gives feedback like too high, too low. This exercise tests loops input validation, logical comparisons, random number generation. But above all, it introduces the concept of stateful interaction, where the program maintains and reacts to user behavior. A great final exercise for Lecture 1. Goal: make an interactive guessing game where the user tries to find a randomly chosen number between 1 and 1000. Here's the structure. The computer randomly selects a number. The user enters guesses in a loop. The program checks if the guess is too high, too low, or correct. When correct, the loop stops and a congratulatory message is shown. We use a do-while loop to ensure the user gets at least one try. Inside the loop, we read input and compare it. We give the user feedback each time, making the game interactive. This is the first real interactive program, where you respond to user behavior and maintain internal state. Excellent work. These exercises were more than just programming syntax. They reflect key principles of object-oriented thinking, encapsulation through methods, control flow, data abstraction, and responsive logic. In the next lectures, we'll scale this up with arrays, classes, inheritance, and polymorphism. But remember, your code will only be as strong as your logic, so keep practicing and try modifying each program slightly to stretch your understanding further. Until next time, code with clarity and design with purpose.